Okay, our goal today is first of all, I'm gonna try one example here. So let's say you have a function fs equals 1 over s plus 3, right? This is the first example. So how do you now find the Laplace transform? Find the inverse rather. Inverse Laplace transform. Okay. Oops. Okay, so first of all, use the partial fraction method. Partial fraction. You get two fraction here because you have two factors. So 1 over s plus 3 equals a over s plus b over s plus 3, right? So what are the factors of this? What are a and b? So let's figure that out. So here you have s plus 3. So multiply this guy by s plus 3. Multiply this guy by s. So you get a s plus 3. So plus bs, right? B times s. Now you have this guy here. So you have this guy here and this guy here. Let's compare these two now, okay? So if you multiply both sides by s plus 3, s plus 3, then they divide out, okay? So you are left with 1 equals a s plus 3 plus b times s, okay? So now this is true for any value of x. This expression is true for any value of s, okay? So you can put any value, then that value should satisfy this equation or expression rather. That's what I meant. Okay, so let's try to do that. So if you put s equals -3, for instance, right? So what do you get? If s equals -3, this guy will be 0, right? So 1 equals b times -3. So what do you get here? b equals -1 over 3. Now put s equals 0 here. If you put s equals 0 here, then what do you get? 1 equals a times 3 plus 0, right? So this gives me a equals 1 over 3. So now you have a equals 1 over 3, b equals -1 over 3. So a meaning a for a over s, right? So this belongs to s and this belongs to s plus 3. Okay, this is just for me. I'm gonna erase this everything now. Okay, so far so good.
Yeah.
Okay. Now let's after that let's use the table. Do you guys have the table? Do you have it handy?
I do, yes.
Okay, so now, so how do you write this? How do you rewrite this guy? Okay, let's rewrite. Then I'll ask you the answer here. So fs. Now my fs is 1 over 3 over s minus 1 over 3 over s plus 3. Okay. So I don't need this anymore, okay? Now let's find the Laplace, inverse Laplace transform of this guy. So what is the inverse Laplace transform of each term on the right? So inverse transform meaning we are trying to find inverse Laplace transform of Fs, right? So that's our goal. So here, inverse Laplace transform of, so 1 over 3 can be taken out, right? It's constant. So 1 over S minus 1 over 3 can be factored out. Then you have 1 over S plus 3. Oops, I forgot something here. Inverse Laplace transform of S plus 3. So now, what is the, look at the table and can you help me to figure out what is the inverse Laplace transform of 1 over S? Just go back. If you have the table here, I have to go all the way here. So here, you 1 over S, what is the inverse Laplace transform 1 over S? 1, right? Similarly, what is the inverse Laplace transform of S plus A? Minus A, right? So here, so you have to use this formula here. You have to go back inverse, okay? 1 over S, 1 over S, and 1 over S plus 1. So 1 over S plus 1 is e to the negative AT, okay? So if you have this formula sheet or table rather, then you can use that table to figure out the Laplace transform here. Here. Okay, so 1 over S is simply 1, right? You already saw that. So this guy gives me 1. Simply 1 minus 1 over 3. And inverse Laplace transform of this guy is, as you saw, is e to the, what is that? E to the minus AT, right? So 1 over S plus A gives you e to the negative AT. I think my tablet died. Okay, let me charge it. Sorry about that. Okay, so here e to the AT, right? So now I have S plus A. My A is 3, right? A equals 3. That's why my answer is minus 3t. So this is e to the negative 3t. So that's why inverse Laplace transform of 1 over S plus 3 equals 1 over 3, 1 minus e to the negative 3t. Guys, any question here? Please? Yes, no, maybe?
Wait, can you repeat what you said? I was just fixing my speaker on my thing.
Okay, so where's the problem? Here? Where's the problem? So here, oops. LJ, please help me to figure out the problem. Where? Here?
I'm not entirely sure where the problem really is.
Okay, so So our goal is, let me repeat it. So our goal is to figure out the Laplace transfer of this this relation, right? So this can be, first of all, our first step is find the fractions. Okay, find the fraction from this one, because we have two factors here, right? We have s and s plus 3. So that's why we have to have two factors here. So by using this partial fraction method, we figure out this guy 1 over s plus 3 can be written as this. So far so good, right?
Yep. I'm
So
listening.
now our goal is to figure out inverse Laplace transform. Okay, so it means 1 over 3 inverse Laplace transform of 1 over s. Okay, this s, then minus 1 over 3, then inverse Laplace transform of 1 over s plus 3.
Okay.
So now if you use the table, right, if you have the table handy, so you can figure out, okay, what is the Laplace transform of 1 over s? What is the
Yeah.
Laplace transform of e to the at? 1 over s minus a.
Yeah.
Okay, now if you have minus here, sorry, if you have plus here, you get minus here. If you have minus here, you get plus here. That's the thing. Okay, so inverse meaning you go back like this. You go back, right? That's the
Yep.
inverse. So what is the inverse Laplace transform of 1 over s? Here, from here to here, backward.
So it'd just be 1.
Just be 1, right? That's what I have. 1 over 3 times 1. Then minus 1 over 3. What is inverse transform of 1 over s plus 3? So this a is 3 in my case, right? S plus 3. So this will be 3 here. A is 3. That's why negative 1 over 3 e to the negative 3t. Because your a is t. Sorry, a is 3.
Yeah, I get that.
Okay. So this is the conclusion. Okay, I didn't do anything. I just rewrote it. So it means, so just 1 over 3 minus. So I just factored this out. Then minus e to the minus 3t. I just rewrote this.
Okay.
Okay.
Also, I forgot to ask. Is this like lecture will be like recorded so we can have it to go through it
Yeah,
again?
I have recorded it, but
All right. Cool.
in case you need it, I'll upload it.
Yeah. Cool. Because I would like to go back through this again.
Okay, sure. All right. So now finally we are in the transfer function. Okay, this is our. So this is the goal of chapter 2, right? So we had to go through all those little details to get to this point. Okay, finally we are here. Our goal is to find the transfer function of the system. First of all, what is the transfer function? Let's define the transfer function. Then we'll do some examples. Okay, what is transfer function? It is the ratio of Laplace transform of output to the Laplace transfer input. Suppose your output is O and input is I. This is your output and this is your input, right? I is input, O is output. Then what is the Laplace transform of output? Then what is the Laplace transform of input? Okay. So assuming all the initial conditions are 0. Okay. So assuming all I, C are 0. So this is called transfer function. Sometimes we represent this by H, sometimes we represent by G. I think the book uses G, okay? So G, the transfer function, is defined as the ratio of Laplace transform of output to the Laplace transform of input. It's like defining efficiency, right? In a simple machine, how do you define the efficiency? Efficiency is defined as output over input, right? In thermodynamics and stuff like that. It's similar thing. So take the Laplace transform of output, take the Laplace transform of input, and you don't call it efficiency, you call it transfer function. Okay, you call it transfer function. So far so good. But think one condition is given there. So you have to assume that all the initial conditions are 0. Okay. So remember when you do the Laplace transform of a derivative, right? What is the Laplace transform of derivative? So what is Laplace transform derivative? You have S, then Laplace transform of function itself plus initial condition. Remember, you have other initial condition. Do you remember from the table? So you have SFS, right? The derivative, right? So inverse transform of what did I say? Oh, sorry. So let me repeat it. So what is the Laplace transform of derivative? SFS plus initial condition there, right? So when you find the transfer function, you don't have to worry about this initial condition. That's what I meant. So you always consider initial condition to be 0. Okay. That's what I'm trying to refer here. That's your transfer function. In general, okay, Laplace transform, transfer function, in general, let me say this way. In general, a physical system can be represented by a linear time invariant differential equation. And those physical systems which are linear and time invariant, they can be modeled by transfer function. Okay, so transfer function is used, okay, let me say this way. Transfer function is used for those kind of system which is linear and time invariant system. Suppose you are given a system, right? Suppose you are given a system which is both linear and time invariant, then you can find the transfer function of this system and you can represent that system. Meaning the transfer function of linear and time invariant system will represent the system. Okay. In other words, a physical system which is linear and time invariant can be modeled by using transfer function method. Okay, we cannot use transfer function for nonlinear system or time variant system. It has to be linear and it has to be time invariant. In that case only you can use transfer function. Does it make sense? But the question is, what is linear? What is linear system, right? What is time invariant system? That's the question now. So let me discuss that now. Okay. So what is linear system? What is time invariant system? So first of all, let me talk about linear. So linear system, suppose you have this is a system. Okay. This is a system. This guy is a system here. Now, suppose the input to the system is x1, output to the system is y1 at time t equals t1. Okay, at times t equals t1, this is your input, this is your output. So at t equals t2, let's say the time the input is x2, output is y2. Okay, if this system, this guy, if this system is linear, what happens is you add x1 and x2. If you add x1 and x2 together, then what should be your output? Your output should be y1 and y2 together. Okay, so what I meant is if you combine the input, you can combine the output. Okay, one more time. If the input is x1, output is y1. If the input is x2, output is y2. Now you combine the input, x1 plus x2, and definitely you will get the output equals to y1 plus y2 because this system is linear. Not only x1 plus x2, you can also multiply this x1 by some number. So 3 and 4 here, I don't know, 3x1, 4x2. Then your output will be 3y1, 4y2. Okay, this kind of system is called linear system. Does it make sense?
Yeah.
So what is time invariant system? Time invariant system is that kind of system. Suppose, let me give you the example that will clarify it. Suppose a time t equals, you know, at some time t, I will call it some time t here. Okay, some time t, okay, you have the input equals xt, then you will get the output equals yt, okay, at some time t. Now another time, I'll take another time now. Another time, I'll take t minus t0 time, earlier, okay? Earlier time, or it could be, you know, plus minus, it doesn't matter, okay? So t minus t0 or t plus t0, it doesn't matter. So in my case, I took t minus t0, okay? At some other time, t minus t0, suppose your input is xt minus t0, then you happen to get y to be, so your yt is definitely yt minus t0. So if the input is shifted in time, the output also experience the same time shift. Okay, that's what I'm trying to say here. So in other words, system respond the same now as it does later or before. Okay, the system responds the same now as it does later, or as it did before. Okay, whatever. So if you have this kind of system that is linear, this is linear, this is time invariant. To deal with this kind of system, we can use transfer function method, okay? That's the condition. If it is linear and time invariant, then definitely we can use transfer function, G. Okay, so now we talked about, we can use the transfer function, right? That's what we did, you said. Now, what does the transfer function look like? Okay, let's talk about that. So let us consider the input is, let us consider output be represented by the nth order differential equation. I know you guys are new to this differential equation, most of you, but don't worry about it because we'll be using the table, right? So we'll be using the table that we already talked about, table. To deal with the differential equation, we'll use table. Suppose this output can be represented by a differential equation like this. So where the differential equation is nth order. So in that case, I can write the differential equation as this. An, which is the coefficient, the nth derivative of ct, n minus 1, and so on and so forth. So let's say, a3e d3c d plus a2 d2c dt square plus a3a2 dc over dt plus a1c. Oh, I made a mistake here, right? I should have said 1 here. This should be 0. Okay, so it could be, so let's say 3d squared c over dt cube, 2d squared c over dt squared minus 1 dc over dt, plus, I don't know, simply c. Suppose this is one differential equation. This is the output. Okay. Similarly, your input is mth order. Okay, this is the mth order. So we are trying to make the difference here. This is m, this is n. Okay, so this input is mth order differential equation here. In general, right? This is nth, This is mth. Okay. Now, suppose this system is linear and time invariant, right? Suppose this system is linear and time invariant, then how do you represent this system in control theory, right? So how do you do that? Let's use the transfer function. So now what is the, so first of all, you have to do the, what is the transfer function? Transfer function is G equals Laplace transform of output divided by Laplace transform of input, right? That's the transfer function. Now let's find the Laplace transform of this guy here. What is the Laplace transform of this guy? Okay, so this is the nth order, right? Okay, so take the Laplace transform of this guy here, which is an s to the n cs. So remember, this is little cs, this is big cs. This is the function, this is the Laplace transform of the function, okay? So if you take the derivative of the function, then you get s, some power to the Laplace transform of the function itself. Of course, an is there, right? It's always there. This is constant, you don't have to do anything with that. So you just keep it. Similarly, Laplace transform of this guy is this guy. And you have Laplace transform of this guy. Then while doing so, you'll get lots of initial condition. Lots of here. A lot of initial condition. Similarly, while you do so here, you'll get exactly similar thing here and a lot of initial condition also. So the good news is that when you define the transfer function, all the initial conditions are assumed to be 0. That's why this whole thing becomes 0, whole thing becomes 0. So in that case, my equation becomes like this: an s to the n, an minus 1 s n minus 1 a0, then cs, you can factor this out, right? Cs is here, cs is here, cs is here. So factor this out here. Cs factor out, then everything else is inside this parenthesis here. Similarly, you can factor out rs from here, rs, and rs. Factor out all the rs and everything else is inside this parenthesis. Now, the ratio of cs over rs is g, right? So divide both sides by rs, then you get this rs cancel out. Then divide both sides by this guy here, again, this guy on both sides. Okay, then you get this cancel out, then you get this, finally this one. This is the formula. Okay, let me do one example that should clarify it. Okay, let's do this example, then this should be fine. So find the transfer function represented by this formula, this equation here. So we are given the differential equation here. Okay, so n equals 1, m equals 0 here. This is nth order, first order, right? Because it could be d to the n, right? On the right hand side, d to the m, right? So I shouldn't say d to the n. So I should have said nth order and mth order differential equation, left and right. Okay, so all right. So now take the Laplace transform of. If you want to find the transfer function, what is the transfer function again? Transfer function g equals Laplace transform of output over Laplace transform of input, right? With 0 initial condition, 0 IC. Okay, so what is the, let's take the Laplace transform of whole thing here, everything here. What is the Laplace transform of this guy? So let's do that. Here, Laplace transform of derivative of c plus 2 Laplace transform of C equals Laplace transform of R. If you want, you can write T inside, which is function, right? It shows that the C is function of T. You can do that too. So what did we do? Take the Laplace transform on both sides. This is our step one. Okay. Now use this rule here. What is the Laplace transform of a derivative? Laplace transform of derivative is S big F. Remember, this is little f, the function. This f is function of time, and this big F is function of S. This is little, this is big, uppercase, lowercase. So here, this is your little c. So what is the Laplace transform of little c? Big C. I don't know. Big C. What is the Laplace transform of little r? Big R. Okay. Now, not only C and R, we have to find the Laplace transform of derivative of C also, right? So what is the derivative of C? The Laplace transform of derivative of C. Use this formula, please. Help me. S, help me here. S, big C, right? Function of S. That's the Laplace transform of this guy here. Okay. So then we also have this term, but we don't have to take care of this guy because we don't have to consider this guy rather because this is initial condition and 0. How do I know this is initial condition? Because this says this is function of 0. 0 means initial state. So see, initial, that's why this is initial condition. This is 0. So you don't have to worry about that. So we have SFS, which is SCS. This guy is done. Now plus 2, this is 2. What is the Laplace transform of this guy? Laplace transform of CT is big CS. Big CS. Equals, on the right hand side, you have Laplace transform of RT is big RS. Right, I'm open for question now.
So f of 0 is just the initial.
Yes.
Gotcha. We just always when we do the transfer function, we just ignore that, just take it out.
Yes, always. Because by very definition, in the transfer function, we always take 0 initial condition. Did I answer your question?
Yep. Sounds good to me.
Okay. Please, any other question, please? So now let me collect the similar terms here. So what do we have here? Little s, factor out CS, right? S plus 2, then factor out CS equals RS. Then now what is your Laplace transform? Transfer function. Transfer function is output over input. So output over input, right? C over R. So how do you get C over R from here? C over R is your G. By definition, G is C over R. So how do you find C over R here? Divide both sides by R and divide both sides by S plus 2. So then this guy cancel out. So you have C over R equals 1 over S plus 2. So this is our transfer function, done. Guys, question here? We figure out the transfer function now.
I'm sorry, would you go over that once more. So the SCS plus 2CS, that equals what's below it. And
So here,
yeah,
okay.
Yeah, I'm a little lost there too.
Oh, that's fine. I think, let me start from here. How about that?
awesome. Thank you.
Let me start from here. So Laplace transform of so Laplace transform of CT is S big CS. So Laplace, and then 2 is 2. Laplace transform of CT is big CS. And Laplace transform of RT is big RT, big RS. Because Laplace transform of function FT is big FS, right? See, little becomes big. So here, Laplace transform of CT is CS. Okay, but we have the derivative here, so that's why. So Laplace transform of derivative is S times Fs. In the same way, we have S times CS. Then Laplace transform of this guy is, which is CT, now obviously CS. Then here Laplace transform of RT, which is big RS. Now you don't have to worry about this condition here because this is initial condition. And while we define the transfer function, right? Transfer function, then we have to always ignore the initial condition. So that's why. So if we have to do that, so don't worry now. Because eventually you are going to ignore it anyway, so why take it now? Okay, so you don't have to worry about this guy. So that's why now let's define the transfer function Z, which is C over R, right? That's the definition of transfer function. So now let's collect C here. Factor out C. S plus 2 CS. I factor out C equals RS. Then divide both sides by R, because my goal is to find C over S, right? C over R, right? So I'm getting C over R here. Divide both sides by R, then divide both sides by S plus 2 also. Then R and R cancel out, this cancel out, divide out. Then you get CS over RS equals 1 over S plus 2. Make sense? This is my transfer function.
1 second, I'm just gonna write that down.
Sure.
But yeah, that makes sense though. I kind of get what you're saying. All right, I just about got it.
Okay. So LJ, can I erase everything now?
Oh yeah, you're good. You're good.
So all right, so now let's do the next part here. So my transfer function is, let me write this down up here. Okay guys, so next, okay, before I forget. So next week we might have the face-to-face class, right? On Tuesday, Thursday. But before that, I'll send you guys the poll. and I'll determine based on that pole. Okay, so I'll send you guys the pole. All right, so now this is my transfer function. So now part one is done, right? Part one is find the transfer function represented by this. So this guy is done. This part of the question is done. Now there is the tail part also. Also find the response CT to an input RT. RT is UT. Okay, input is RT obviously, but we are given input here. Okay, our output is not given, which is simply CT, right? But input is given. Input, which is represented by RT, it is given to us, which is UT. So what is UT? What is UT? Help me to define UT. It is 0 for t less than 0, and it is 1 for t greater than 0. Okay? So that's my UT. UT is 0 for all values of t less than 0, meaning negative t. And UT is 1 for all values of t, positive value of t. Okay? That's my function UT. So input is given to me. Now, find the response function assuming the initial zero condition. Zero initial condition. So we are assuming initial condition, zero initial condition, meaning our system is linear. This implies that our system is linear and time invariant. Most likely, right? So now you'll see. Okay, now what do you need to find? You need to find the response C. Now you need to find C here. C is not given. RT is given, C is not given. Transfer function is there. So how do you find the C from here? So what is G, by the way? G is C over R, right? So then C equals Z times R, right? Okay, so CS, RS, right? So that's your CS here. So what is your G? G is S plus 2. What is your R? We don't know yet, right? Do you know R? No, because we know little r. So how do you find big R from here? Remember the Laplace transform of 1 is 1 over S. Okay, so because ut is basically 1, because when it is 0, Laplace transform is 0, obviously, right? So when ut is 0, Laplace transform is 0. When ut is 1, Laplace transform is 1 over, yeah, so basically we are adding 0 plus 1 over S, which is 1 over S. So that's why I can rewrite this guy as this. 1 over S plus 2. What is your R? R is 1 over S. Because your R is UT. Little r is UT. That's why big R is 1 over S. Guys, question so far?
Wait, so big R is like based off of UT or RT?
Big R, we don't know big R,
Okay.
but we know little r.
Okay.
Little
So,
r is, go ahead.
so us knowing little r allows us to replace big R? Is that what you're saying?
Little r, so All right, this is a good question. Very good question. I love that. So what is the definition of G? Big C over big R. That's the definition. Okay, we cannot change the definition. This is fixed.
Mm-hmm.
We are not allowed to change the definition. This is fixed. GS is big CS over big RS.
Mm-hmm.
Okay. From here, how do you find C? C equals G times R, right? GS, you can write GS here. You can write RS here. Okay.
Yep. I'm with you.
So do you know GS? It's already found, right?
Yep.
First part one of the problem.
Yep.
So GS is 1 over S over 1 over S plus 2.
Yep.
Then RS is RS.
Yeah.
Okay. Now we need to figure out RS. Can I figure out RS? We are given little r. Okay, little r is given here.
Mm-hmm.
Little r is UT.
So are you saying if you take the Laplace transform of the little
Yeah. Big R is called Laplace transform of little r.
Oh, okay, I got
Big
you.
R, the name of big R is, it's very long name. Laplace transform of
That'd be of little r.
little r is called big R.
Mm-hmm.
Okay. So we are given little r, then
Mm-hmm.
find the Laplace transform of little r. So little r is UT, right?
Mm-hmm.
It's given. So what is UT? UT is
So how
0.
did you figure out what that UT was like? So UT is equal to 0, T less than 0, and all of that. How did you figure that out for UT?
Okay, this is the definition of UT.
Oh, okay, got
Okay,
it.
instead of writing this whole thing,
Mm-hmm.
so mathematicians just write UT.
Okay.
So when I say UT, this should come in your mind all the time.
All right, sounds good.
Okay, so now since I know little r, so how do you find the Laplace transform of little r? Meaning big R. How do you find big R from little r? So you have Laplace transform of 1, 0. Laplace transform of 0 is basically 0, right?
Yeah.
So that's why Laplace transform of 0 is 0. Then Laplace transform of 1 is 1 over S.
Mm-hmm.
So that's why. So Laplace transform of, so this is the conclusion. Laplace transform of 1 is 1 over S. Laplace transform of U is also 1 over S.
Oh, okay, I got you.
Okay. So that's why. So my U is R, right? So, or you can say big R here. Big R is 1 over S.
Mm-hmm.
Now let's plug in here.
Mm-hmm.
So RS is 1 over S.
Mm-hmm.
So now you have your C equals, let me write this down here. Your C equals 1 over S plus 2. Okay, let me erase this everything now.
Hmm.
Okay, now you have to figure out C here. From this you have to figure out C. All right. So this is C is function of big S, right? So this can be rewritten as S plus 2.
Mm-hmm.
Okay. So let's find the partial fraction of this guy here. What is 1 S plus 2? What are the factor of this guy? Did we do that before? I think we did similar though. I remember, or something similar, but not exactly. So I'll do it again. No worry. So what is the fraction of this guy? Simple fraction, partial fraction of this guy. So A over S plus B over S plus 2, right? So how do you take the LCM of this thing here? So here you simply multiply by S plus 2 on the top and bottom. You multiply by S on the top and bottom here. Now your denominator is same. So you have A times S plus 2 plus B times S divided by S plus 2. So equals 1 over S plus 2. So far so good. Now these two cancel out. So 1 equals A s plus 2 plus b times s. Now you need to figure out a and b. So put s equals 0, then what do you get? If you put s equals 0, then this is gone. Then you got, this implies a, excuse me, this implies 1 equals a times 2. So this implies a equals 1 over 2. Now plug in s equals negative 2. If we put s equals negative 2, this guy becomes 0, right? Negative 2 and plus 2. So 1 equals 0 plus, then s is negative 2. Negative 2, this implies b equals negative 1 over 2. Now I can rewrite this guy here. So my a is, what is my a? My a is 1 over 2. My b is negative 1 over 2. That makes sense so far? So I found the fraction.
So you just did the partial fraction, and then that's just replaced your numerators.
Yep.
Okay.
So that's it. Now, what you need to do now, you find the inverse. Your goal is what? Your goal is figure out little ct. How do you find ct from cs? That's your goal.
The past.
So meaning, do the Laplace transform, inverse Laplace transform, right?
Yeah.
Your inverse Laplace transform of, what is this guy? That's your goal. Inverse Laplace transform of c, meaning you are trying to find little ct. That's your goal. So in that case, you do the inverse Laplace transform of this guy here. Inverse Laplace transform of this guy. What is that? So 1 over 2 inverse Laplace transform of 1 over s minus 1 over 2. Remember this minus here.
Mhm.
Then inverse Laplace transform of 1 over s plus 2. So far, so good.
Yeah, I got it.
So 1 over 2. What is the inverse Laplace transform 1 over s? Look at your table again, right? What is the inverse Laplace transform of 1 is 1 over s. Laplace transform of e to the, what is that again? E to the minus at is 1 over s plus a. Remember we used this formula before? So from the table, I need these two formula. Okay. So now you are doing the inverse, right? Since you are doing the inverse, you go backward. So what is the inverse Laplace transform of 1 over s? What is the inverse Laplace transform of this guy? So we go backward. Inverse Laplace transform 1 over s is 1. And 1 over 2, inverse Laplace transform 1 over s plus a. Here a is 2. A is 2. That's why this a is 2. So e to the negative 2, e to the minus 2t. So conclusion. So ct equals 1 over 2, factor out, e to the negative 2t. That's what we are supposed to find. See? Also find the response ct. We did that. Right? Question here, please. Thumbs up, thumbs down, question.
Yeah.
Oh, I have a,
I completely got it.
oh, Saad, you have something for me?
So far, so good, sir.
Okay, very good.
I'm good.
Okay, thank you. So let's move on, right? All right. Now let's talk about a specific case of Laplace transfer function, particular system rather. Okay, let's apply this transfer function to particular system, physical system, particular physical system. Okay, so in this case we start with electrical system now, electrical network. We start with electrical network. So to understand that, so we need some basic concepts before I go there. I don't want to directly jump in there. So before we go there, I want to introduce some basic concepts, okay? So consider three passive linear component, for instance, resistors, capacitor, and inductor. So when we talk about electricity, right, electric circuit, so these components come in your mind. You have resistors in the circuit, you have capacitor, you have inductor. Okay, these are the three basic, okay? Now, now let's figure out the voltage current relationship in the case of resistor. Okay, in the case of resistors, in the case of capacitor, in the case of inductor. So similarly, let's figure out voltage charge relationship in the case of resistor, in the case of capacitor, in the case of inductor. Then similarly figure out impedance relationship. Again, so we care about everything here, the relationship under zero initial condition, because when you talk about transfer function, you assume that initial condition is zero, right? So that's what we do. Okay. So now if you want to do the transfer function, so I'll give you the list of this relationship before I move on to the real problem. Okay. So you already know that, was I just so I want to refresh your memory. Okay. So what is the voltage current relationship for in the case of resistor? You know that, right? In the case of resistor, voltage current relationship B equals IR, right? That kind of stuff. Similarly, in the case of capacitor, what is the voltage current relationship? Inductor, what is the voltage current relationship? I'll give you the table, okay, for that. So everything I have a table, okay. Now let me come to the point here. So once I give you this table, now you can figure out the transfer function of the system, okay. So what are the steps to find the transfer function? First of all, you have to write the differential equation for the circuit. Let's say you have the circuit like this. You have resistor and you have capacitor for now, okay? You have resistor and capacitor like this. This is plus, this is minus of the battery, this is R, this is C, right? So for this circuit, now find the differential equation. What is the differential equation for this circuit? For this guy? What is that, okay? That's your first step. Then figure out input and output. So what are you supposed to submit? Looks like this is your input, right? This could be input, or could be something else too. We don't know. Then are you supposed to find the voltage across this? Suppose this is your input, right? Suppose this is your input, and you are supposed to find voltage across this. Then that voltage is your output, right? And this is your input voltage. Okay. So this could be 5 volt. This could be 3 volt. I don't know. Right? So this is your output, this is your input. That's what I'm trying to say, okay? So figure out input and output and modify the differential equation accordingly, okay? Because what I'm saying is, when you write a differential equation, it can have all those, so it can have this value there, you can have, okay, so you can, okay, you will have this in the differential equation. You will have this in the differential equation. You will have this in the differential equation. You have 3 things in the differential equation, right? The differential equation, you have 3 things. 1, our resistor. This is 1. This is 2. This is 3. Now, so now everything you have to choose 1, 2, 3. All those 3 in terms of input and output now. So how do you change this guy in terms of output? Okay. or input, whatever. Input, everything has to be in the form of input output. Okay, that's what I'm trying to say. Figure out input output and modify accordingly. Then after that, step 3, take the transform of differential equation. When I say transform, I'm saying this Laplace transform, okay? We're not talking about anything else. Then finally solve the transfer function. Find the Laplace transform and define the transfer function, which is output over input, right? So C over R. So once I do one problem, it will be clear. Okay, let me do one problem, then it should be just clear to you. So should we do one problem? All right, so before we do the problem, let me give you the table. Remember, I promised you to give you the table, this table here. So I promise you to give this table. So this is the table I'm talking about. So in the case of capacitor, what is the voltage? Let me begin with resistor because that's easy one, right? You already know that. So in the case of resistor, what is the voltage current relationship? Look at this column here. This is voltage current relationship. So for resistor, you have Ohm's law, right? Because IR or RI. Then what is the current voltage relationship? You simply, divide by R on both sides. You get I equals I over 1 over R T. That's your current voltage. Then what is the voltage charge relationship? B equals Ri, right? Ri. So I is dq over dt. From here, you can find the charge, right? So charge and voltage. That's the voltage charge relationship. Okay, similarly, impedance is R. And what is the admittance? Admittance is reciprocal of impedance, okay? If this is R, this will be 1 over R without doubt, okay? Just take the reciprocal, okay? These two guys are easy, okay? They take the reciprocal of one another, okay? That's how you do it. Now, similarly, for the capacitor, what is the voltage current relationship? For the capacitor, voltage current relationship is this here, this guy. V equals 1 over C, 0 to T. Okay, this is T, by the way. 0 to T, I tau d tau. Meaning, do the integration of I, okay? Then divide by C gives you voltage in the capacitor. Similarly, how do you find the current in the capacitor? C, do the derivative because we have integration here, you have derivative here, right? So similarly, voltage charge, this is voltage charge relationship, and impedance is 1 over CS, and admittance is CS. Similarly, inductor, we have B equals L di by dt, I equals this, and B equals this, and impedance this, and admittance this. Okay, so this is just the table. You already know this thing, right? This is physics 112 again. This is physics 112. All right, so okay, before I go to now one more thing. Before I go to the real problem, so let me find the inverse Laplace transform of, or I would say, inverse Laplace transform of voltage current relationship. So in the case of resistor, right, let me begin from here. In the case of resistor, what is the formula for voltage and current? Because IR, okay? So how do you do the inverse Laplace transform of V? Little b becomes big B, and T becomes S. That's the inverse Laplace transform of left-hand side. Sorry, Laplace transform of left-hand side. What is the Laplace transform of R? So R is not function of, R is constant, right? That's why it stays R. R is not variable, it's the constant, so it stays the same. Then what is Laplace transform of I? Little I becomes big I, function of S. Okay, that's what I have here. V equals Ri. Okay, Laplace transform of this guy Oops. Okay. Laplace transform of this guy is this guy. Guys, help me here. What is the Laplace transform of this voltage current relationship for the case of, in the case of capacitor? Help me here. What is the Laplace transform of little v? Big V. That makes sense, right? So 1 over C is constant. We don't worry about this. 1 over C. This is constant. Now, what is the Laplace transform of integration? Look at the table and can you tell me what is
Is it
the Laplace?
IS?
Excuse me?
Is it IS?
I over S.
I over S. Okay.
Derivative is IS. You're
Okay.
almost there. Yeah, derivative is IS. If I had this di over, dt, right? Then it would be, oops, si or is. But you are talking about integration here. If you have the integration, then you have to divide by s instead of multiplying by s. So I over s.
I got you.
Okay. So that's the Laplace transform of this whole thing here. Then similarly, what is the Laplace transform of this guy here? Laplace transform of B is big B, right? The L is constant, no change. And what is Laplace transform of di over dt? As you said, LJ, so now is.
IS, okay.
Because this is derivative, right?
Mm-hmm.
Now, having said that, so I know the Laplace transform of all those voltage current relationship. Now having, okay, excuse me. Now, let me find the, let me define a transfer function like this. Okay, now I'm excited. Since I know this is my Laplace transform, right? Based on this, how do you find G? So let me define a transfer function, okay? This is a new transfer function now. G is new transfer function. So how do I define this? G is Bs over Is. In the case of capacitor, what is your G? Help me here. In the case of capacitor, what is your G? What is Bs? Bs is 1 over Cs times I. Then what is your I? I is I. So they cancel each other. So you have 1 over Cs. That's your G in the case of capacitor. So what is the, in the case of resistor, what is your G? GR in the case of resistor. Again, B over I. So B is Ri and I is I. So it's simply R. Okay, R is R. In the case of inductor, what is your GL? So help me here. In the case of inductor, you have L as I divided by I. I cancel out, you have L over S, LS. Okay. So impedance here, Z here is 1 over CS. That's my conclusion. G here is simply R. G here is LS. Okay. So I'll keep this in mind. I'll come back to this after I'm done with the, oops, one problem that I'm supposed to do. Okay, let me do this problem, then I'm done for the day. Okay. So remember the steps, we talked about different steps here, right? Here, these steps. Okay, we'll be utilizing these steps now. These steps in a problem now. Okay, that's what I'm trying to do. Okay, here is the problem. This is the problem. So find the transfer function relating the capacitor voltage to the input voltage Vs. So first of all, find out, so how many components are there? we have three components, L, R, and C. What is your output? Guys, help me here. What is your input? That's your first step. Figure out output and input. Guys, you might have to help me here, please. Oops.
Would the input be VT?
Yeah, BS, right? Yeah. Yeah, input, yeah, BT, yeah, good. Input is BT. So input is BT. What is output? Output is BC, right? Because it says transfer function relating capacitor voltage to the input voltage. The transfer function, how do you define transfer? Laplace transform of output over Laplace transform of input, right? Okay. If your input is Bs and transfer function is given, then this should be your output, right? So BC is your output. Okay. So we figure out what is output, what is input. Now let's write the differential equation for this one. So what is the differential equation? So to write differential equation, use the KVL, Kirchhoff's voltage law. So summation V equals 0, right? In the loop. Help me. You go from here to here. Let's start from here. You go up. So you have BT, right? BT, positive. Then what else? What is the voltage drop here? What is the voltage drop there? L di over dt, right? That's my voltage drop here. Then what is the voltage drop here? Ri. And what is the voltage drop here? 1 over C, 0 to T, I d tau. That should be equal to 0. But we haven't chosen the sign here yet. Let's choose the proper sign. How much time do we have?
I think we're out of time.
Oh, really? So let me quickly finish this line only, okay? Then I'm done. So what is the sign of this guy here? This guy negative, because we are going from here to here, right? So this is, then what is this guy? This is also negative. Actually, this is also negative. Okay, so we did the first step. We have the differential equation. Step number 1 is done. Then we'll continue, other steps next time. Unless you have any question, I'm done for the day, guys.
Real quick question: when is that homework due again?
Oh yeah, so don't worry about the homework because I haven't talked to the IT people yet. Okay, don't worry about it.
Okay, sounds good.
All right.